Hello students, we are now in the next lecture, which happens to be the lecture number 20, and in today's class we are going to look into the details of how to understand the equation that we have at the end of the last class. So basically in the last class we have solved a problem, and the problem is basically consisting of a linear charge. So that is what is shown here. You can follow the white color cursor now. So you have the charges that are distributed uniformly on a wire. So it is like this. And then there is a point here P, which is a distance Z away from this. So basically if you are going to see the vertical distance from the wire, it happens to be the Z. So the question or our aim of the last class problem is to calculate the electric field at this particular point P. Let us say that this is a point P here. If you want, you can represent it by a point P. And the question is that we are interested to evaluate what is the electric field at this particular point, which is a function of this particular distance Z. And the important point in the last class is that the wire is of finite length. That is very important. So this is uniformly distributed on a wire of length 2L. So of course 2L is just written in order to say that symmetrically we can consider this is the 0. The center point can be 0, so that the left side, the total, on the left side you have the length L, and on the right side also you have a length L. Okay, so 2L is not very much. If you don't want a 2L, you can keep it as a total length L. So that is not a problem. 2L is given in the question paper. That gives you an idea that the center of the point can be taken as 0. So if you are going to consider that this is 0, then minus L, this can be taken as minus L, and this distance can be taken as plus L, and so that you can consider that this distance is 2L, which is the length of the wire. So 2L is only an informative, or it is a suggestive information saying that it is symmetrical about the point 0. Okay, it doesn't matter that you have to take only 2L, you can put any length. Okay, so remembering this point, now we have this equation. So after doing the calculation, we finally arrived at this particular equation, namely the electric field at the point Z. So the diagram is, that is why I am showing the diagram. For detailed diagram, you can always see the last class one. So in the last class, we have drawn a bigger diagram explaining all the variables. So now just to refresh your memory, I have drawn a short diagram like this. So you have E of Z equal to, we have this expression 1 by 4 pi epsilon naught. I am not cancelling this 2 and 4 because it is easy to realize the existence of 1 by 4 pi epsilon naught. That's the reason. So you have 1 by 4 pi epsilon naught multiplied by 2 lambda L. So how do you understand? So how do you understand the 2 lambda L is that this is what we are going to see, that 2 lambda L can be easily understood as total charge. So what is the meaning of that? You already know what do you mean by charge density. So the definition is this: charge density, linear charge density is defined as, this is the definition that you have. The definition says that how much amount of the charge that you are going to take, and you tell me on what kind of length you are going to distribute. So let us say that I am going to distribute over a length L, then that will be the lambda. So now in our problem, you see how do you get 2 lambda into L. 2 lambda into L is actually nothing but 2L times L. So you have to understand like this. It is lambda into 2L you have to say, because 2L is our total length. So in our problem, this small l equal to 2L. So therefore we can understand 2 lambda L as the total charge that is present in the system. So we have a total charge Q that is present here, and then you have some expression which depends on both the length of the charge distribution as well as the distance at which you are going to calculate the electric field. So you cannot clearly tell. So what I am trying to say is that these are the points you are going to note down. So this is the first point. The second point is that you can't say that the electric field is proportional to 1 over r square. This is not observable. This is not right. So is this point clear? You are unable to see you can't say exactly electric field is proportional to 1 over r square. Here r is generic distance. So if you are going to consider that z is the distance, for example, but however, as you can see that there is a z square plus l square is there, even though there is a power half here. Okay, if l is not there, then you can imagine that this will be z and that will be another z, then 1 by z square will come, but that will be a special situation. So for the time being, you can't say that the electric field is proportional to 1 by r square. If you are not comfortable with r, you can always say z, because z is our distance for the time being. In our problem, z is the distance. So therefore, the meaning of this into mark, I have put an into mark here. The meaning of this into mark is we are not able to observe the 1 over r square behavior. That is because, of course, you should remember that it is not a mistake, or it is not something that is contradictory. The point that I am trying to explain using this into mark here is that, so this is E doesn't go like 1 over r square is not true here. And it is very much acceptable because electric field being inversely proportional to the square of the distance is valid only for point charges. So this point should be clear to you. So what I am trying to say is E is not proportional to 1 by r square is meaningful because we don't have a point charge. It is an extended charge. Okay. So the reason is this is because we have extended charge. So you should remember that electric field is inversely proportional to the square of the distance is valid only for point charges. So I am now giving the emphasis between the point charges and extended charges. Extended charges means the charges are present from the point x equal to minus L, that is here. You can follow this white color cursor. Okay. The charges are present all the way from x is equal to plus L to x is equal to minus L to plus L. So everywhere charges are present. That is why we are using the word extended. Whereas in the case of the simple Coulomb's law, it is a point charge. Point charge means only at a particular point like this, you have a charge q. So this is called a point charge. So the charge that you are going to have here in this particular, our problem is an example of an extended charge. So that is why we use the word distribution. Extended charge distribution. So whenever you don't have the point charge, you cannot expect 1 by r square behavior. That means you cannot say that electric field is inversely proportional to square of the distance. That statement is no longer valid. So this is an important point that we are noting from the solution to the previous example problem, and we are going to do more understanding. So now what we will do is we will ask the question, what happens if the length of the charge distribution is infinity? Suppose you yourself ask the question, what if, you can ask this question, what if 2L goes to infinity? 2L goes to infinity means, well, L goes to infinity. That means we are going to have an infinite charge distribution. So the answer to this question can be obtained easily from this particular equation. So let me write down that this is equation number 1, so that you can follow this one and then simplify them. So the meaning, what do you mean by L approaching infinity, is to say that L is, that is, in this particular case, we can say that L is much greater than Z. We can consider that because you are going to consider that 2L is approaching infinity means you are going to take L approaching infinity, and therefore this L will be much greater than Z, which means that if I am going to write L by Z will be much greater than 1, that gives you Z by L will be much smaller than 1. So we need this kind of analysis, because why do you want this Z by L or L by Z? Why do you want this comparison? Is the reason is that if you look at if you are going to see equation number 1, you have the variables L and Z. So that is why we need to compare them. Otherwise, there is no need to compare. So what we are trying to say is that this is the meaning of the statement that L approaching infinity in equation 1. So this one, use this particular expression or use this kind of situation in 1. That is in equation number 1. So then what will happen? So let us write down then what will happen here itself. So electric field at a particular distance Z due to an infinitely charged distribution will be equal to, so let me write down like this. This is 2 lambda divided by 4 pi epsilon 0, and this L I will write down here. So L divided by, so there is a Z here into, so now this is the point where you have to think. We need Z by L. So you can now understand what we have done. Since Z by L is much less than 1, we need the equation or we need an expression Z by L in equation number 1. So if you see equation number 1, we don't have Z by L, but we can bring Z by L into picture by pulling out some expression. For example, if I take an L square outside here, what will happen? So if L square is taken out, then I will be getting 1 plus Z square by L square. Okay, so that's what exactly we have done here. So here this 2 lambda by 4 pi epsilon naught is which is written, only this L can be written here. So I will be getting L divided by, here you pull out an L square, but since there is a power half here, L square becomes L, then this becomes 1 plus Z by L whole square. What is an advantage of writing like this is that since Z by L is much smaller than 1, this particular quantity is negligible in front of 1. In front of 1 means in comparison to 1. So in comparison to 1, numerically Z by L whole square will be very small, and therefore you can neglect. So if you neglect that, then what is remaining, you can easily write down that this will be equal to, we'll say that this is 2 lambda divided by 4 pi epsilon 0 into, so here you get this L and this L get cancels out, these two things get cancelled out, and then Z by L is neglected, which means simply you delete that particular term. Then what is left out is simply you get AZ divided by, only this particular Z is remaining, and that's all. So this is the expression for the electric field at a point Z. But now what is the difference between this equation and this particular new equation number 2 is that this electric field is valid due to an infinite charge distribution, linear charge distribution. Okay, if you are going to change the structure from the wire to the circular or to a triangular configuration, then these things are not valid. So just remember that whatever we are discussing is only for a charge distribution along a line, because the original diagram is here. So this one you have to remember. So you have from minus L to plus L. Now you have asked the question, or you have extended the minus L to plus L to minus infinity to plus infinity. So remember, that is the important point you should remember, because this is the point number 3 we are discussing. So in the point number 3 we are asking the question that this is due to, so this discussion is very important because the appearance of the equation is now somewhat very simple. So you compare this equation number 2 with equation number 1. Anyway, it is not fitting in one board, so I will be going up and coming down. So just to have a look at equation number 1. This is your equation number 1. Okay, this looks little not complicated, but little lengthier expression because it contains both L. There is L here. There is Z also present. Both Z and L are present. Here also L is present. Here Z is present. So now when you are making a special situation that the length of the charge distribution is infinite, then you see that the length L has disappeared into the equation. That is what you are going to note down. So in equation number 2, you see that here L is not present. So which means that The equation, this is what we mean to say that the equation is independent of the length of the wire, because length of the wire is infinitely long. So that doesn't enter into an equation. If it enters, it's a problem only, because if the L appears in the numerator, then it is infinitely large. If L appears in the denominator, then it is 0, because 1 by infinity. So in both the way it is not present. That means it is independent of the length of the wire. So this is true only if the charge distribution extends from minus infinity to plus infinity. So therefore equation number 2 is a special case, and you have to note down. So this is the third point. These are the points that we are noting. So this is the third point. Now within this point, we further note down one more thing. What are you noting from this equation number 2 is that, what is that you are going to note from equation number 2 is that the electric field is now proportional to 1 by z. Okay, not proportional to 1 by z square, because this 1 by z square is something coming from the Coulomb's law, right? 1 by r square. You always remember that electric field will be inversely proportional to the square of the distance. So this is, once again, the point to be noted is that the electric field is now not inversely proportional to 1 by r square, but instead it is inversely proportional to 1 by z. So that is clearly here. But in the previous case, it is neither of that. You can't say whether it is 1 by z also, because that equation is a little bit more complicated, that it contains z also, it contains l also. We can't say that it is 1 by l, we can't say whether it is 1 by z, because it's a combination of that, and here also you have an l. So we can't say. So when you are coming to a particular special situation of infinite charge distribution, there is something special. The first thing is that the electric field is independent of the length of the wire or the length of the charge distribution. This is the first point. And the second point is that the electric field is inversely proportional to distance, not square of the distance. So these points are important because in the competitive examinations, for example, they will give 4 options. Electric field is inversely proportional to, or electric field is square, that is inversely proportional to square of the distance, or cube of the distance, or 1 by root z. Like this, 4 options can be given in the competitive examination. So at those times, you need to do this kind of analysis and then realize which is correct. You can't say that always the Coulomb's law is valid. So once again, I will specify that Coulomb's law will not be valid, because Coulomb's law is valid only for point charges, and equation number 2 is for infinite charge distribution. Okay, so this is the interesting result. So we will make one more interesting result. So this is the point number 3, right? So we will now consider point number 4. So point number 4 is, I'll write down here. So let us not make infinite charge distribution. So point number 4 is like this. Let the length of the rod be finite. Let L be finite, so that will not go to infinity. So that let it be finite only. But let us go far away. But let Z goes to infinity. Z going to infinity means what? You go very far away from the wire or from the charge distribution. So you can understand what is this from the diagram. So let me again go back to the top of the screen. So here you can see what is Z here. So this is Z. Z approaching infinity means what? You are going to stand here at the point P. That means now you go away from this in this direction. You keep on moving until you are going to be practical infinity. Once again, remember, infinity means practical infinity, which means large distance when compared to the length of the wire. Length of the wire is not, we are not at all disturbing it. Let it be minus L to plus L, that we will not disturb. And only this particular place of the point P is changed. So that means you are going away from the charge distribution, far away from the charge distribution, and then you are going to measure what is the electric field. If you measure, what will happen to equation 1? Equation 1 is here. So you should remember the equation 1 and then you have to simplify. Okay, so I will again go down here so that you can now write down what will happen under this condition. If L is finite but Z is tending to infinity, then you have to ask the question, which ratio will be large. So you can easily say that L divided by Z will be much less than 1. Because here itself you can see L is a finite. So that is in numerator. Z is infinity. So Z is in the denominator. So when you are going to divide them, it should approach 0. So it should approach 0 is what we say very small than 1. Why the number 1 has to come here is because this is the general thing. See, if you have something like x square plus y square, why the 1 is coming here? That's what I'm explaining. The reason is like this. If you take an x square common here, what will happen? You get 1 plus y square by x square. That's what you get. So that can be written as x square into 1 plus, then you say y by x whole square. So basically there is a 1 coming here. So the 1 is coming in comparison to the y by x. So there is a 1 and there is a ratio y by x. And between them you have to compare which is big and which is small. So whenever an equation is there which has an appearance of x square plus y square, then a number 1 will come and then a ratio will be there, something by something. Here it is y by x. So you have to compare two numbers. 1 is one number, y by x is another number. So you are going to ask the question whether 1 is much greater than y by x or whether 1 is much smaller than y by x. Such kind of question you are going to ask. And depending on that, you have to simplify the equation. So that is why when we are saying that L is a finite number and Z is very large, by infinity remember that it's very large. You take it as 1 lakh or 10 lakh or 1 crore. So that doesn't matter. It is only a large number that you are going to take. In such a situation, L by Z is going to be much smaller than 1. We are not interested to say that L by Z is approaching 0. Approaching 0 is true, it's correct only. But in our equation, this particular 1 comes into picture here and therefore we need to compare with 1. So therefore, even though this is correct, that is L by Z tends to 0 is correct, we need a better representation that L by Z is much less than 1 is a better comparison for our equation. So now what you do is use this in our equation number 1, because equation number 1 is valid for finite Z and a finite length. So therefore, now you substitute that. So therefore, what I will be getting is, let me write down that E of Z will be equal to, so let us write down that this is equal to 1 by 4 pi epsilon 0 into 2 lambda L divided by, you already have a Z. Now I am going to take a Z square outside. But remember that there is already a square root. So Z square becomes Z. Then into L by Z whole square. Then plus 1. Then you have to the power half. And then of course unit vector is there. I'll write down here itself. And that is the AZ unit vector. So now you can see that, this should not disturb you. So let it be like this. So as you can see, whenever an equation looks like this, you will have to bring it to the form 1 plus y by x whole square or 1 plus x by y whole square. You can also bring x by y, because instead of taking x square common, you can also take y square common. Isn't it? Both are same. So you can also write like this. This is same as y to take x square common, you can take y square common. If you do that, then what will happen? Then I will be getting an x by y whole square plus 1. So both are equivalent. But now you have to analyze whether you have to use the first version. First version means this version. Is this the one which is suitable, or is this the one which is suitable? That you have to decide. That decision is to be taken based on this condition. That is why I am repeatedly coming to this point. This condition is very important. You have to think which condition is now suitable for us. Okay, we are now going to a situation where the length of the distribution is finite and Z is going to be very far away. In that case, L by Z should be much smaller than 1. And therefore, we have to bring L by Z. You see here, L by Z has to come into picture. In such a way, you have to take this outside the bracket. And once you finish that, let us simplify this equation. Then we will be getting 1 divided by 4 pi epsilon 0 into 2 lambda L divided by Z square into AZ. And well, that's fine. Now we can understand now further. Let me put a box for the time being. Once again, I am not cancelling this 2 and 4 because 1 by 4 pi epsilon naught is something, let it be there. So that will be more comfortable. And this is your equation number 3. Now here there is something interesting. You have to see something interesting from this solution, final expression. What is interesting in this equation is that what we note here is 2 times lambda times L is nothing but 2L times lambda, which means linear charge density multiplied by the total length. That should be the total charge. That is the meaning of 2 lambda L. So that is the total charge that is present in the total charge that is present in the wire or whatever linear material that you have taken. That's the meaning. The second thing is, this is the first point. The second point is, and in addition to that, we are going to observe that the electric field is now proportional to 1 by Z square. You see this? 2 lambda L is what? Q. So 1 by 4 pi epsilon naught into, this is Q. So Q by Z square. So therefore, electric field is therefore proportional to 1 by Z square. You can see how different it is. Like in the previous case, just now you have seen that electric field is proportional to 1 by Z only. Here you see, electric field is proportional to 1 by Z only, but not, and it is not proportional to 1 by Z square. That is the previous result. And now you are getting the other way. And now the result is different result, namely that the electric field is proportional to 1 by Z square, which looks like the Coulomb's law itself. And therefore you have to think a little bit, how is this possible? Because Coulomb's law is generally valid for point charge, and equation 3 is not for the point charge. Okay, that is clear, right? Equation 3 is valid for what kind of charge? That you should know. You see here L is finite. So L is finite means, so therefore you should also remember that this is for finite charge distribution. And what do you mean by finite charge distribution is, it means it is not a point charge. You should remember, finite charge means the length is finite. By finite you can say, let us say 2 meter. 2 meter is finite. So over a 2 meter distance you spread charges. That is the kind of thing. You take a 2 meter long some wire and then put the charges uniformly over its length. So that is an example of a finite charge distribution over 2 meter. So it is not at all a point charge. Point charge means only one point. That's all. So when it is not a point charge, I am not at all expecting 1 by Z square. I am not at all expecting. But it is appearing as 1 by Z square now. So that looks something surprising. So therefore, you have to think, how is this really possible, or why the equation is now showing that electric field is proportional to 1 by R square behavior. Why is it so? So if you ask this question and if you think a little bit, then immediately you can get the answer. So now you will see what is the answer. It is very simple. That only thing is that you have to think. Once again, I'll write down that L is finite. L is finite and Z tends to infinity, or we say that it is practically very large. That is the meaning, very large when compared to L. So that is, what is the meaning of this statement, this infinity, is that Z is far greater than L. That is the meaning. So that means, as an example, practically you have to speak in terms of some numbers, because when you are going to perform an experiment, for example, if I am going to take 2 meter wire as the length, you have to choose a distance which is much larger than 2. So instead of 2 meter, you go to 2000 meters, for example, 2000 meter. 2 meter is the length of the charge distribution. 2000 meter is the place where you are standing away from the wire. So you now agree that 2000 is much larger than 2. Such a number you choose, and then there you have to go and stand and measure the electric field. So which means that in terms of diagram, how does it look like? Let us see that is, so let me draw this. So this particular distance is 2 meter. So let me say that is a 2 meter distance, for example, which means that this is the wire that you have. So you have a wire which is of length 2 meter, but however, I am going to move away, far away. That means 2000 meters I am going to move. Say, so this is the place where I am going to move. So this is the point P at which electric field is calculated. Whether it is calculated or whether it is measured, that's all. That's both are same. So right now we are doing the calculation. So this particular distance that you have, so whatever you have written is this 2000 meter. So that is from here to here. So finally what happens? You have to think now carefully. You are now, when you are standing near to the wire, you can see the length, or 2 meter long wire you can see. And when you go far away, 100 meter, 200 meter, how the wire will look like? You won't feel that length. You feel as if it is a small dot, isn't it? Even though it is a long one, when you are moving away, 2000 meter means 2 kilometer. Okay, just imagine if you go 100 meters away and you look at the 2 meter long one, you won't feel it like a 2 meter. It's a small bit. It will appear as a 1 inch small bit. And if you go further and further, if you go up to 1 kilometer distance, you can't even see. Practically, you can't even see. Even if you are able to see, it looks like a dot. So it looks like a dot is something which is important. That means what I am trying to say is, I'll write down here, this so-called 2 meter wire looks like a dot from 2 kilometer distance. Okay, first of all, from 2 kilometer distance, you will be unable to see. That is a different story. So let us assume that you are able to see it. If you are able to see it, it will look like a very tiny dot. That's all. Which means that whenever you are going to observe an object from far away distance, that object looks like a point object, not like a distributed object. And therefore, coming back to this equation, electric field is 1 by z square, means that as far as the calculation of the electric field is concerned from large distances, any extended distribution will look like point charges. That is the meaning. The meaning is extended charge distribution, which means that this kind of a 2 meter long wire, this is called extended. This extended charge distribution will appear as if it is a point charge. This is the conclusion from the analysis. So our conclusion is, this is the conclusion. If L is finite and Z is infinity, then extended charge distribution looks like point charges. And therefore, since it is looking like a point charge, you again go back to the Coulomb's law, namely the electric field is inversely proportional to R square. That's what is that you are having the result. So our final result, which is the final result, we have equation number 3. So the equation number 3 is the final result corresponding to the situation where the length of the wire is finite and Z is very large. Practically, we are going far away from the wire. In such a situation, the electric field behaves like a point charge only. In which case, what is the total charge that is present is 2 lambda into L. This is important. 2 lambda L will be the equivalent to the total charge. So you can always replace this by Q. You can read like this, 1 by 4 pi epsilon 0 into, this is Q. So Q by Z square. Like this you can read. So this is these are the 3 important conclusions that you can get it from the solution to the problem that we had in the last class. Okay. So we are going to do further analysis. So let us know what we will do is, we can understand this still better by moving to the cylindrical coordinate system, and then we can come back to the Cartesian system. By doing that, we can understand more about the equation number 1. So you should remember what we are doing in today's class. We are taking the solution that we obtained in the last class, and we are trying to understand that in a better way, or more and more details can be extracted from that particular equation number 1. That's what we are doing. So now what we will do is, we will consider how we can move from Cartesian coordinate system to cylindrical polar coordinate system for the same equation number 1. Okay, problem is not changing, same problem that we have in the last class, and the same solution, which is equation number 1, but how to move from a coordinate system, namely Cartesian, to the cylindrical, and how to come back. By doing that, what is an advantage? So that we are going to continue now. So till now, whatever we have discussed, namely the original equation, which means the equation number 1, and the two special cases, all the three of them I am now summarizing at a single point or a single place here, so that you can compare and contrast each one of them, and then note down their special features. Namely, in the first case, you can't say that it is inversely proportional to 1 by Z, neither you can say 1 by L. Whereas in the case of the infinite charge distribution case, you can clearly say that the electric field is inversely proportional to the distance from the wire, which is the 1 by Z here that you have. And in the second case is that we have a finite charge distribution, but we are standing far away from the wire. In such a situation, the electric field is inversely proportional to 1 by Z square, and 2 lambda L is taken as, or it is same as the total charge present in the system, which means that the finite charge distribution really looks like a point charge when it is seen from far away distances. So that's the overall conclusion that we have for the problem that we started in the last class. And especially out of the three options that you have here, the equation number 2 appears to be very simple when compared to all the three of them. The 2 appears to be simple. Of course, the 3 is also simple, but however, 3 is very identically same as the Coulomb's law itself. So there is nothing special. It doesn't appear to be something special. It really looks like Coulomb's law itself, because this fellow is Q. So just Q by R square is there. So that is why 3 doesn't have any special importance right now. Okay. Whereas 1 is little bit complicated, slightly, and therefore when compared to these 3 equations, equation 2 appears to be somewhat a simple equation, and it is also a special case corresponding to an infinite charge distribution, in which case the total length doesn't enter into the equation. That is first point. Second point is electric field is inversely proportional to 1 over distance. Now what we will do is, there is something that is important. This is not the way that you can finally make a conclusion quickly, because right now you are having a coordinate system which is Cartesian. So if you are going to see the diagram that we started with the last class, we started with the Cartesian diagram. So the coordinate system that we were using is basically a Cartesian coordinate system. And AZ, what do you mean by AZ unit vector? It is the unit vector along the direction of Z. Then you ask the question, what is that Z here? And Z is the distance from the wire. So if I am going to roughly draw a diagram, anyway, proper diagram is there in last class thing, but if you are going to draw a rough diagram, so if that is the wire that you have, starting from minus L to plus L, and if this being the origin 0 here, then this is the Z direction that if you are going to choose that this is the Z axis, then automatically this direction, so this particular direction will be the unit vector AZ. So that is what we understand. What is this AZ? Then why do you want to do this understanding is that you ask the question, why this Z axis is why should we give the name Z axis for this? Why not X, Y, etc.? You can also say X or Y or Z, any one of them you can keep. So is there anything special, or because of that whether we lose any information? That's what we are asking the question. We should not lose any information because of the choice of the coordinates. Just because you have chosen the Z axis, for example, you should not lose the detailed information. That is what I am trying to explain you. So in order to analyze whether we are able to grasp the entire information from the problem, you yourself ask the question that why this should be z-axis? Why can't something like x comma y? So instead of having some preferred choices of the axis names like x, y, z, you ask the question that what happens if it is neither z-axis nor x-axis nor y-axis. That means it is any point on the space which doesn't really falls on the x, y and z-axis. It can be anywhere other than the x, y, z axis. So in such a situation, how this particular diagram will look like, because the diagram is drawn in such a way that z-axis is coinciding. That is what we have chosen as a special case. But suppose if it is not coinciding, how the equation number 2 will look like, whether it is going to have the similar form or it will change. So in order to understand that, we can see if you can tilt this particular wire like this. Suppose this is the distribution that you have from minus L to plus L, for example, here, and the center is here. And then we have chosen this particular vertical axis as the z is the distance that we have chosen. So suppose this point is chosen as the z, and we have calculated the electric field at this particular point is z. That's what we have done. This is this diagram. So this the same diagram is I am rewriting here in order to see a three-dimensional perspective. Suppose if you are going to draw a circular path around this particular point. So this is the center. Center is there. You can follow the white color cursor. So that's the center, and this is the electric field point. And suppose if you are going to draw a circle or a circular path, keeping this as the radius, then you can see that kind of diagram will look like this, isn't it? So that can be like this, something like this. Okay. So what is the information that you are gaining is that if you are going to draw a line like this, for example, then this distance is also z. So you can say that this is also E of z, because this is a circular path. If this distance is z, then this is also z. We are not saying z-axis. It's only a distance is z. So whether you are going to measure in this direction or in this direction or in any other direction, for example, here, if you are going to measure in this particular way like this, so along this is also z, because this is a circular path, which means that irrespective of, so there is nothing special. So we are asking the question that in the previous diagram that we have chosen a particular point here, this is the P, and say that electric field is calculated at E of z. So this particular point that is shown here has nothing special. So you can choose any point along the circular point. You can see this is the circular path. So I am putting dots here. That means any dot that you are going to choose on the circle, for example here, or for example here, these are the points. Everywhere or any point along this particular circular path is at an equal distance z away from the wire. Therefore, this particular equation 2 is valid. That is the conclusion that we can draw if we can draw like this. That means if you are able to see the three-dimensional perspective, this particular z need not be z-axis. It can be any distance. That is the meaning. It need not be z-axis. For example, if you are going to draw like this, that cannot be z-axis. Only the vertical one that you have drawn can be z-axis. But however, this one need not be z-axis. Therefore, this vector cannot be az unit vector. Similarly, this particular direction will not be az unit vector. This particular direction will not be az unit vector. These are not az unit vector. Whereas if you choose only the proper vertical one, this is the proper vertical one, this will be the one having the az unit vector. So I am talking about this particular thing. So what is the special about the z-axis, and why you have to attach az unit vector to the equation number 2? That was the question that we asked. And based on this analysis, that means simply understanding the diagram from a different angle, that is a different perspective, we understand that z is any distance from the wire, and az need not be along the z-axis, but it can be anything along the circular path which shows the radius of the circle. So what you understand is that there is a circular path coming into picture, and the direction of the z corresponding to the direction of the radius, because these are the radius. If you show like this, that is the radius that you are going to measure. Now, since circular path is coming and radius is entering into picture, clearly you are able to visualize a cylindrical polar coordinate system rather than a Cartesian system. So even though we have started with our problem with the Cartesian coordinate system, it appears that cylindrical coordinate system would be a better choice for the problem under consideration. So this is the meaning, or this is what we understand by further for if we try to understand equation number 2. So equation number 2 is correct. There is nothing wrong. This equation is correct only, but we can understand in a better way if we can write down the equation number 2 in the case of the cylindrical polar coordinate system. So by understanding this, we can write down that equation 2 in cylindrical system. How do you write it is, there is no need to do any conversion, because the diagram gives you this diagram. This diagram is very important. If this diagram is not there, you don't know why we are writing. This is how you started with. This is how you started our problem solving, and then we made a conclusion. Our understanding is like this. Our understanding of the previous equation number 2 implies that we need a polar coordinate system, because circle is coming into picture, and the circle can be drawn anywhere. It need not be here. You can also start from here and then draw another circle like this. You can draw another circle like this. You can move to another point and then draw another circle like this. Therefore, if these two circles are joined here, you are able to see a cylinder. So basically, therefore, a cylindrical coordinate system appears to be a better choice for this. And if you see what is the z in this equation, the z represents the radius. This is nothing but this is the radius of the circle. And this particular z is also radius of the circle. This particular z is also radius of the circle. So everything is radius of the circle. And what is the direction of this one unit vector? That is your a rho. So you already know what is the symbol. So if rho is the radius of the circle, then the unit vector will be a rho. And therefore, equation 2 we are going to rewrite. That's what we are basically doing. So equation 2 can be written in the cylindrical polar coordinate system like, so let us write down like this. So equation 2 is the same as the electric field. Now we'll say that instead of z, because we have z is the symbol that we were using till now, and now based on the new diagram we understand that z represents the radius of the cylinder, and the standard symbol for the radius of the cylinder is rho. Therefore we write as E of rho equal to, then the rest of the equation number 2 is same, that we will write down 1 divided by 4 pi epsilon 0 into 2 lambda divided by, now here you can see that this particular z becomes rho, and then the unit vector becomes a rho, and that's all. So that is the equation, which is the same as the equation number 2, but however this particular equation contains more information. In what way it contains more information means, you are now able to calculate the electric field at this point. You can calculate at this point. You can calculate at this point. You can also calculate at this point. At all these points, which means on the surface of the circle or on the surface of the cylinder, you can calculate the electric field using this equation, which is equation number 2. Whereas if you are going to use this particular, the previous version of the equation 2 using Cartesian system, you think that it is valid only for one point as in the previous diagram, that is this diagram. So you think that it is only valid here. If you are going to come here and ask what is electric field, you think that it is something that has to be recalculated. But now you think that if you are going to follow a circular path, then along every point on the circular path, the equation is valid, and therefore the electric field takes this particular expression. So this is our important and notable conclusion, that the choice of the cylindrical coordinate system is more important in order to extract more information from a given problem. And we make a conclusion that the problem, thus we say that the problem therefore possesses cylindrical symmetry. the problem has cylindrical symmetry, which you are now only visualizing. It is already there. Only thing is that we have not put effort to visualize it. Now we are able to see that it has a cylindrical symmetry, which means that if you are going to keep a wire like this, then surrounding this particular point like this, you can draw any two circular path. If you draw and then join them like this, you can feel a cylinder surrounding the wire. This is your charge distribution. This was your original charge distribution that we have been discussing from the last class. So you are able to see or visualize a cylindrical surface in such a way that the axis of this particular cylinder is coinciding with the charge distribution. And basically what all you are doing till now is you are calculating the electric field at this point. So at this particular point you are calculating the electric field, and that is what you are calling E of Z. But now you understand that it would be better if you can call E of rho, because rho is the radius of the cylinder. The advantage is that the same thing can be copied here, 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 etc. So anywhere on the circular path, I'm putting dots, right? You are able to see those dots. So everywhere, wherever, whichever be the point that I'm going to calculate, everywhere you'll be having the same value of the electric field. You can calculate anywhere on the circular path. And the measurement is from the center. The center means from here you have to measure. From here, if you measure only, you can get the radius of the cylinder. So similarly, for every point you can repeat this procedure, and that is what we mean to say that the problem is possessing cylindrical symmetry, and therefore this particular equation naturally evolves in the cylindrical polar coordinate system. This is very important. And whenever you want to convert this cylindrical system to the Cartesian system, you can always do that. Okay, so remember that equation 2 is in cylindrical coordinate system. So you can convert. So equation 2 you can convert to Cartesian system if required. No, it is not at all difficult, but whenever it is required, you can convert. And remember that you should not say that equation here, we have already written one equation here. This is not the equation that is valid for all the points. It is valid only at one particular point shown in this particular case. Suppose if I am moving a point like this or moving a point like this, then you don't know how to calculate. Therefore, the equation number 2 that was originally written down with a Z here and a Z here is valid only for one particular point. If you are going to move the point, then you have to redo the calculation. So that is the place where there is it's a shortfall of that particular notation, and that is why we have come back to this cylindrical coordinate system. So remember, what I am trying to say is converting to Cartesian coordinate system means it is not going back to the old equation. That is not the meaning. It is the conversion where the rho, phi and the z in the Cartesian system should go to the appropriate x, y, z. If you do this conversion, then you will be getting all the three variables x, y, z corresponding to this particular expression. Namely, this is the new equation number 2 corresponding to the, why I am saying new equation number 2 is it is corresponding to the cylindrical. The old equation number 2 is corresponding to not necessarily the complete Cartesian system, but it is valid only for z-axis. That is important. It is valid only along the z-axis. To that extent, it is correct. But if you say that I am moving away from the z-axis, then that is not at all valid. You have to redo the calculation. So in order to avoid that redoing the calculation, we can easily convert the new equation number 2 to the Cartesian system. And the conversion is not difficult because we have already seen what is the cylindrical polar coordinate system, and therefore you can always convert. Converting means if you have a rho and a phi and a z, for example, these are the unit vectors that you have. These are the unit vectors that we have in the case of the cylindrical polar coordinate system. You can therefore easily convert it. That is equal to, you have to put an appropriate matrix. This matrix also we have defined or we have derived in our previous class, that you have to refer to some of the previous classes, maybe lecture number 3 something like that. Lecture number 3, 4, at that time we have seen the conversion of the Cartesian to the cylindrical polar coordinate system and then multiplied by the Cartesian systems. Here you put Cartesian Ax. So this particular equation is already available with you because we have done it in our previous classes. Maybe lecture number 3, 4 that you have to check. It is there, but the matrix is a simple matrix that you can write down, that this is cos phi, sin phi, 0. Then you put a minus sin phi, cos phi, 0 and 0, 0, z. So this is the simple matrix that is required if you want to convert a Cartesian unit vector to the cylindrical polar unit vector. So you can always convert like this. So what is the meaning of this? Is not very complicated. It looks like that, but if you multiply, you see what is a rho here. This gives you a rho unit vector is equal to, you multiply. This is cos phi into ax. You write down that this is cos phi into ax cap plus sin phi into ay plus 0 into az. 0 is not there. Then the remaining thing is a phi and az. So we have 3 unit vectors. Out of that, the first one is written down. Similarly, you can write down the second one, a phi equal to, similarly az equal to. But however, there is something interesting. However, you don't require all of them. Why you don't require all of them is, in the equation number 2, you see this, in the new equation number 2, only a rho is present. See here, this one, only a rho is present. A phi is absent. A z is absent. Therefore, you don't have to worry about those equations. That is why I have written only a rho in the equation. So therefore, now you take this equation and then substitute. But before doing that, we have to understand, or we have to rewrite this cos phi and sin phi in terms of x and y. So you need to know what are these two things. So once you know that, then you can use the equation for the a phi and then simplify, and that takes only 1 or 2 lines. It's not difficult. And we will see what is this question mark we have written. For this, what you have to do is, you have to do a simple thing, that rho is given by square root of x square plus y square. That is one thing that you know. And the second thing that you know is that tan phi will be equal to y by x. Because these are the 2 things required for the Cartesian to the cylindrical polar coordinates conversion, and we need what is cos phi. That is what is our question mark. This question mark is what is cos phi, but cos phi is not there here. You have a rho here and tan phi is only available. Cos phi is not available. Therefore, you have to calculate the cos phi, and that is fairly simple, because what all you have to do is you draw a triangle representing the tan phi here. So if I am going to draw a triangle like this and put a phi here, this is phi, and then tan phi. So tan phi would be equal to y by x. So this should be y, that should be x. Then only this is tan phi. So now tan phi equal to y by x, that's coming. So therefore, what should be this one? That should be x square plus y square with a square root. So that is the distance that you have. And therefore, from this triangle, now we will come in this direction. From this triangle, we can write down what is sin phi. So sin phi would be equal to y divided by square root of x square plus y square. And we can also write down what is cos phi from the same triangle. So cos phi would be equal to x divided by square root of x square plus y square. So now you see that we got sin phi and cos phi. So we start from the standard equation, the conversion of the Cartesian to the cylindrical, namely rho equal to this tan phi, and corresponding to tan phi you draw a triangle, and from this triangle you get sin phi and cos phi, and this value of the sin phi and this value of the cos phi you substitute here, because I put a question mark here, right? There you will have to substitute. So you substitute that, then I will be getting a rho. So let us write down that. So therefore a rho equal to, so I will go to the next. Therefore I want this one. So therefore a rho unit vector would be equal to cos phi into, so which means x divided by square root of x square plus y square into, so what unit vector was there? it was a ax unit vector, right? It was a ax unit vector. Then you have a plus sine phi. Sine phi is y by square root of x square plus y square into ay. And that's all. So which means that you got the conversion from the cylindrical system to the Cartesian system. So you have the a rho unit vector. This is what you have to substitute. So let us say that this is the equation number, which I don't know what equation number we will keep. So we'll have to see. We have this one. So this is the new equation number 2. This is the place where we are going to substitute. So let us substitute that. So let us substitute in new equation number 2. Okay. So therefore this will be 3. So substitute this in new equation number 2. Then we get, so electric field, we can say at the point rho is given by, electric field at the point rho is given. The other things are same. Now you write down that this will be equal to 1 divided by 4 pi epsilon 0 into 2 lambda by rho. And what is rho? You know, rho is actually square root of x square plus y square. Okay, into a rho. A rho, this entire thing you copy. The a rho is this one. It is x times ax by square root of x square plus y square plus y times ay by square root of x square plus y square. And that's all. So remember that this particular square root of x square plus y square is for rho. It is there in the previous screen. So you have to verify that. Just remember it. See, it is here. This one. This rho equal to square root of x square plus y square. That rho only I am going to use it in place of the equation number 2. So here. This is the place where I am substituting. And then this rho also we will be changing to the corresponding x comma y. So we will see that now. So once you have substituted, you got the equation that looks like this. So almost we have done. There is nothing to simplify more. We can now write down that this is equal to 1 divided by 4 pi epsilon 0 into 2 lambda into, we can say like this, these two we can multiply, that's why I am writing like this, x into ax, this is a unit vector, plus y into ay unit vector. Now after multiplying this, you get a common denominator, so I will be writing that x square plus y square. And that's all. So this is the expression that you have. We can write down like this. It is lambda divided by 2 pi epsilon 0 into xax plus yay divided by x square plus y square. So the electric field at any point x comma y is equal to. So what is that x comma y I am writing here is that this particular rho is basically x comma y. Because you should remember that if you are going to draw a circular path like this, and if you are going to choose any point here and say that this is x comma y, then if you are saying this is the center of the circle, and if you draw, that will be the rho. So specifying a particular point by the cylindrical polar coordinate system rho is equivalent to writing down x comma y in the Cartesian system. So therefore rho is equivalent to x comma y. That is the meaning, because on the right hand side we have removed all the unit vectors of the Cartesian. We have removed all the unit vectors in the cylindrical system, and we brought ax and ay. Ax and ay, they are, what are they? They are the unit vectors in the Cartesian. That is the reason I am writing x comma y here. So this is our conclusion, that we have now successfully converted the equation number 2 to the Cartesian system. So this is same as equation number 2 in Cartesian system. And okay, we can give equation number 4. Give this. So this analysis is very important. So what is that your understanding is very important. What are you understanding after doing all these things? Is that this equation, namely the new equation number 2, this one I am talking about. If you are going to write down in the cylindrical system, it appears like this. It appears in a much more simpler form, because the problem is possessing cylindrical symmetry. Your equation is also in the cylindrical coordinate system. That is why it looks simple. Now problem is possessing cylindrical symmetry. I am going to write the equation in the Cartesian, means it is going to look a little bit lengthier expression because of the transformation between the coordinate system. That is the reason. Other than that, the equation is identically same. Remember once again, equation number 2 that is written here in this box is identically same as what we have obtained as equation number 4. So equation number 4 is identically same. It's not a new equation. It's identically same, but it represents the same scenario in the Cartesian system. So this is very interesting. The reason why it is important and interesting is, once again I would like to emphasize, what is that we have done is that if you are going to have a charge distribution like this, if this is the wire that you have a minus L, 0, plus L. So that is the length of the wire. And if you are going to go straight up like this, if you are going to straight up like this, we say it is z-axis. Okay, that's fine. And you are choosing a point here, and then we are calculating E of Z. So that was fine. E of Z we have done it in the last class. That's fine. Now after doing all these things, Cartesian system, converting to polar, etc., what is that you have achieved is that if I am asking the question, instead of this point, can you calculate the electric field at this point? If you ask this question, this is neither z-axis. Remember, if you draw a line like this particular line, this line is neither z-axis nor x-axis nor y-axis. It's none of the three axes. Then how are you going to calculate the electric field at this point, which is represented by E of x comma y? So that is the question. So for this you can use equation number 1 that we have derived in the last class, or in the today's class we have rewritten. That's also you can use. So you can use equation number 1. Now if the question is that you want to calculate electric field at some point which is arbitrary point x comma y. Arbitrary point means a point that does not lie on x-axis, a point that does not lie on y-axis. It also does not lie on z-axis. It is lying somewhere else, and that is an arbitrary point. For such a point, the calculation of the electric field is given by equation number 4. So that is what we have. Our calculation is this. So by doing all these things, you finally have to understand something, that using this particular equation, we can calculate the electric field at any point x comma y. See, at any point x comma y, not necessarily on a particular axis. But remember, x and y is present, but where is z? Z is missing, right? That you should ask where it is. It is not difficult. The z-axis is this one. So remember that. Naturally, what happens is z is missing means it will not miss actually. This would be the z-axis. So you are going to fix the charge distribution line, that is the wire itself will be fixed as the z-axis. Then x and y will be any point in the surrounding space. So any space, whether it is this point or that point or this point or a point here or a point here, everything is x comma y. Only thing is you can say that will be x1 y1, this will be x2 y2, that will be x3 y3, etc. But any point that is surrounding the wire would be some kind of x comma y. And the electric field at any surrounding point can be calculated now using equation number 4. So now you understand how we are able to visualize the system and then convert from one coordinate system to the other coordinate system. So this understanding is very important, because given a problem at that time, you'll have to think, and then any kind of transformation you should be able to do. And the transformations are basically done using the matrices. They are known as the transformation matrices, which we have done in our lecture number 4 or 5, I don't know, 3 or 4. And typically this one, for the case of the cylindrical to Cartesian, this is the transformation matrix. So if you know the transformation matrix, then that's all. You can easily convert from one coordinate system to the other coordinate system. Now, before making a conclusion, just I would like to show one question from the IIT JAM joint admission test for the MSc, right? IIT JAM, and let me show you that one. Yeah, here it is. So this is JAM 2016. Okay, so this is the IIT JAM 2016. Let us see first question. Forget about second question. You see the first question alone. So if you read this, you have an infinitely long wire. Uniform charge density lambda is there, and you consider that particular wire itself as an z-axis. Then the question is, you see there, then the question is, calculate the electric field at any point a comma b. Okay, a comma b, okay, away from the origin. So if you calculate, what would be the electric field? That is the question, and you have the 4 choices A, B, C, D. And now you can see that you can easily see what is in the answer. That if you see, this is taken as A and this is taken as B. So in the IIT JE, IIT JAM, it is written as A comma B. So instead of saying X comma Y, they have written A comma B. So naturally all these things you convert it as A comma B. So this should be A square plus B square. That should be A times AX plus B times AY, and that's all. So you have the solution to that particular problem, and the answer is given by B. Isn't it? So that is the answer. So based on our analysis of a simple problem, and based on the understanding of what kind of symmetry present in the system, and overall we got this particular answer. It is not necessary that you have to go through 1 hour of the work to get it, but I am explaining you in such a way that you can understand step by step, and as you understand, you can quickly solve and get the problem done. Okay, so that's the idea. So finally we have the answer. The answer to the problem is actually B is the answer. So with this we will stop. So in the next class, what we will do is, we will continue with this particular problem once again and make an introduction to the polarization, electric polarization, and then we will see how to get the expression for the electric displacement vector. That we will do in the next class.